Hello, this is called a Yupana or an Incan Abacus. And before I start trying to show you how it works, it is extremely different from the way any kind of Western mathematics works. It's not based on the decimal system or the zero. You can use it with the 10-base system for addition and multiplication. I don't know if whoever invented it back in ancient times had that idea of wanting to be able to have it be used with a 10-base system. It's taken me a long time to even start to grasp how it works. So basically, in order to understand how to use it, you have to throw out pretty much everything you know about mathematics and start over again. When you're dealing with normal decimal math using the 10-based system that we use, you're going to have certain numbers that are easier, right? If you're multiplying and dividing and adding and subtracting and you're using 5s and 10s, it's far easier to do problems than it is doing things by 7s or 8s or 6s. This, as far as I know, and as far as I know, is fairly ancient. It seems like it was in use far before at least the decimal system reached Europe. It's 40 based, so if you understand what that means, as we have in normal mathematics, we have 1s, 10s, 100s, 1000s, 10,000s, and so on. It leaps in multiples of 10. This doesn't work that way. It goes in multiples of 40. It's 40 based. It's also, on top of that, it's based on the what do they call that? And you can see it right here: 1, 2, 3, 5, and it would go on 8, 13, and so on. It's what we call what's it called? Not Pythagorean theorem, the Fibonacci sequence. So there's another calculating device I'm going to make a video on later. I'll just show it to you right here. This is called a Mancala. It's from Africa. Depending on what language, there's going to be a different word for it, and there's going to be a different word for the type of math depending on what language, there's going to be a different word for the math that is done on this. Oh, it probably looks like a Mancala game, and it is. It's the same concept. You put rocks in here, and you can multiply and divide really quickly. You can add and subtract really quickly. Mancala is a pretty popular game, but I could never find any videos that show you how to use it to make mathematic calculations. So I'm going to make a video on that too, hopefully, and several other ancient calculating boards, calculating devices that exist. This one, just to go through it quickly, it's binary. It works on binary, whereas this Yupana works on what the West supposedly discovered, some guy named Fibinacci supposedly discovered the Fibonacci sequence. He didn't. It was being used by the Incas a long time ago. It's also used in computer programming, and this binary system from Africa is also used in computer programming. I think they both are. In computer programming language, which is just natural mathematics that happen in nature. It's just it's like truth values or something in philosophy. Something's either true or it's not true. It's just part of nature. Something's either logical or it's not. And this is kind of the same way. It's nothing like a decimal system. So if there are people out there that watch this video and they know of more people or more information on this in particular, I'd be curious, but I never could find anything about it. My wife figured it out. I did find some clues on how to do math on it. Now looking at it, it's kind of like, duh, you know. But this is 1, this is 2, this is 4, this is 8, this is 16, this is 32, this is 64, this is 128, 256, 512, 4024, or excuse me, 1024, 2048, 4096, 8192, 8,000 something, and 16,000 and something. I got it in front of me here. This is 16,348, 32,768. And you might think it's kind of weird numbers. Why not have it be different numbers? But if you're going to use a decimal system and attempt to apply it to binary mathematics, it's not gonna end up well. You can see is right here now. If you use an octal instead of a decimal system, which basically is that you count up to 8 and then you start at 1 again, then it's gonna look a lot different. So hopefully I'll get into that in a different video. There are, even though you can't really see it now, there are similarities between the Mancala and the Yupana, and they are both binary. So with a binary system that the Mancala uses, each whole is equal to and one more than all of the holes behind it added together. And it's actually pretty simple. I'll show you a simple problem. I'm 1. Well, I want to multiply 1 2 times. So I just move it forward. And we have 2 holes. So we've multiplied 1 2 times. And it works the same way. If I want to take 16 and I want to multiply 16 by 2, I just move forward 1. What if I want to multiply 16 by 3? What if I want to multiply 16 by 4 or something like that? So if I want to multiply 16 by 2, I move forward 1. I've just doubled it. If I want to multiply 16 by 4, I move forward once, and I've just doubled it, or quadrupled it, because this is 64. You see what I mean? So if I want to multiply 16 by 3, I multiply 16 by 2 by 4, and then by 1 more. Like a normal multiplication, 16 times 1 is 16. So if you were going to multiply, this whole is 16, if you're going to multiply 16 by 1, you're simply multiplying 16 by itself and you have 16. Okay? If you want to multiply 16 by 2, you simply move it forward 1, and you've multiplied it by 2. You've doubled it. If you want to multiply 16 by 4 by 3, okay, you move forward 2 spaces, you multiplied it by 2, by 4, or excuse me, if you want to multiply 16 by 3, you would multiply it by 2, and then you multiply it again by 1. You simply add these two wholes right here. It's 32 plus 16, and you just add those up. It might sound really simple, but you know, it is actually, for doing big numbers, it's nice, and you can make this as big as you want. If I want to multiply 16 by 5, so let's just go through it. We're going to multiply 16 by 1. 16 times 1, 16. We're going to multiply 16 by 2. 1, 2. 32. We're going to multiply 16 by 3. 1, 2, 3. And then you add those two up. We're going to multiply 16 by 4. 1, doubled, and then quadrupled. Okay, it's 64. We're going to multiply 16 by 5. Doubled, quadrupled, and then by 1. So you have 16 plus 64. Multiply 16 by 6. You would continue on doing it that way. So it's an interesting device. Honestly, that's all you need to know, and you can use it. But I want to do a video on it later. I also have this I want to do a video on later. Can't quite get it all into the camera there. Let me put it sideways. So this is extremely simple, and if you teach your kids math on this, it's for addition and subtraction. It's called a taptana. It's also from the Incas. Supposedly, it seems like something that would have been from Europe. I don't know, because it uses a 10-base system. But this is your tens column. It has 9 holes, and that's your 0. So this is your tens column, your ones column, your tens column, your hundreds column, your thousands column, and your 10,000s column. Really, when we're counting, we only use 9 digits. We don't use 10 digits. 10 is a placeholder. The 0 is a placeholder. So basically, you just real quick, 1, 2. I want to add 2. I have 2, and I want to add 4. Or I got 1, 2, 1, 2, 3, 4. It's 6. It's pretty simple. And so, of course, you can keep adding. But if I was going to add, let's say I was going to take the number 7, and I was going to add 5 to it, I would count up, and because I have filled this up, I would put a rock in my 0 space, because that's what that hole up there is for, and I would count 5. 1, 2. I would put a rock here, because that represents we've passed the 10 mark. That's actually an 11. 1, 2. I put a rock in the 0. That's 10, actually. That's 11, right? And then I keep counting up. 3, 4, 5. Okay, so you can see pretty simply how that works. 7 plus 5 is 13. So it's basically 10 and then 3 more. And so you just continue that on in these columns. And for me, honestly, to be able to see the problem laid out in front of you visually is far better. I wish I would have had this when I was a kid. The way mathematics is done, not only do there's just so many problems with it, but one of the problems is that when you're learning the math, you're not actually visualizing anything in front of you unless you're doing geometry. The math it's just so abstract, and it's boring. Okay, so let me try to introduce this thing to you, because it's a lot more complicated than those. You can see actually how simple. They're extremely sophisticated and simple. Both of them are. They're amazing, actually. So to explain this, basically, this row, believe it or not, adds up to 39. I told you it was 40 based. How does this row add up to 39? And you just, I don't know if there's any other way you'd figure it out now. They teach this to children now in Peru and Bolivia, and I don't know what other countries, but they teach it completely wrong, and they teach the kids that this row equals 10, but it doesn't. It equals 11. I mean, you can see there's 5, and there's another 5, but that would be 11. And then they say, oh, that's a placeholder like a 0 and stuff like that. And you can use it like that, and you can do addition you can do addition and subtraction like that. But the big board I just showed you with all the holes in it, that's what they used for addition and subtraction. They didn't need to use this. As far as I know, this is only used for multiplication and division. It doesn't work very well for multiplication and subtraction if you're going to use it the way that at least I believe it's supposed to be used. I've studied it enough to where I'm not going to get onto the history of it. Maybe later in another video I can, of how this came to be, how people know about it. All of the theories and all of the mathematicians that have written books on it. There's many theories about how it works, and no one's really reached closure. And they do teach it in the schools. In my opinion, they teach it wrong. And so maybe in a later video, I'll go into all the history and all the where it came from. But in short, there's no received knowledge from any Incas that used it as to how it works. The only reason we have this is because of some medieval picture that some conquistador drew. He was an artist, he was a historian, it was like a Catholic priest or something, and I remember his name. His last name was Poma or Palma. I think he might have been Italian. He's either Italian or Spanish or Portuguese or something, but he drew a picture of it, and he said that this is how the Incas do their math. They use this little thing, and their mathematical techniques are far superior to the Europeans, and they can do huge calculations very quickly on it. But then he never explained how it works. And as far as we know, no one of them ever told anybody how it worked, which is weird. It's hard to believe that no one ever passed on the knowledge of how to use it. So then there's been years, many years of books written, 200 years of books at least. Several books have been written by people claiming that they figured out how to use it. I haven't looked too deeply into it, but I do know that and if you're going to try to use it as a 10 base, you can't do multiplication or division on it. And if you're going to use it the way I'm going to teach you, that I think it's supposed to be done, maybe you can do plus and minus on it. I don't know, but I'm not too worried about that because it doesn't interest me. Maybe we can. It would be interesting. Now, there's people that try to show you how to do it, but I don't believe it, that they're doing it right. So let's get into it. This row here equals 39, and this dot here equals 40. So I'm going to show you, I drew a little graph here. I hope you can see that. Maybe I should zoom in a little bit on it. Got this super professional operation going on here. Okay. So why this is called a 40 base, let's just start with this row here. This is 1. This is 40. This is 1600. This is 64,000. So you get these by multiplying 40, and you multiply 40 by 40 and it's 1600. You multiply 1600 by 40 and it's 6400. Now, if you're not interested in this sort of thing and this looks extremely complicated and difficult, fine. For me, I'm extremely fascinated. And just like with the Mancala, how the numbers look arbitrary and why do the numbers add up to that, it has to do with our decimal system that we use nowadays, and that these methods of doing math that I'm showing you are extremely ancient. They're far more effective, and they're used in computer. This is what all computers, if you have a phone, the phone I'm using right now to record this, uses this form of math to make its calculations. It does not use the stuff you learn in second grade, with your plus and minus and multiplication in the decimal system. No computer ever used that, and it couldn't use that. So we're getting back to something that's really ancient and original, and that's used in computer science. And it's way older than any computer. And these are kind of an ancient form of computer. So the reason these numbers seem off, like why isn't this 150 or something, or 10 or 100, and why isn't this 1000? It's because they're not using decimals, and these people didn't use decimals. Like I explained, they're using what we call the Fibonacci sequence as far as the Yupana goes, and that's not decimal. And the same with the other thing I showed you. They're using binary. And so you can count easily by octal, and it ends up looking nice and even instead of having all these odd little funny numbers here, 128,000, 192,000. It looks a lot better with more even numbers when you use the octal system, at least on the other one. Now with the Mancala, if you use an octal system which counts to 8 and then starts over again, you wind up with something that looks a lot cleaner and it's easier to add and subtract. But we'll get into that later. And so the octal, an octal base system, which is an 8-base system, goes with binary counting, like the Mancala. Now with the Yupana, I don't even know which of those with the octal or whatever counting system. It could be a 12-base or something, but for our concern, it's a 40-base. And then after that later, I want to get into the Mayan system, which uses a 20-base. So basically, in the world, the major bases that have been used by cultures have been, there was the sexagesimal system of the Babylonians, the Chinese and Egyptians, I don't know, ancient India, I don't know, but they say that the decimal system came from India, I don't know, but the Romans had the whatever they called them, the Roman numerals. That was basically a 5-base system. 5 and 10 is kind of the two bases that they use, whereas the sexagesimal system was 60, but it's divided into 3 groups of 20. The Mayan system is 20, and it's divided into 4 groups of 5. And it does make a great difference in the way you do calculations, even though it might not sound like it would matter that much. So you can kind of see how that works. Now, let's move here. As you see, this is 1, this dot is 2. So each dot, it doubles. Now, as with the Mancala, every hole equals all of the holes behind it plus 1 more added up. With the Fibonacci sequence, every number in the sequence equals the 2 numbers that are behind it. Okay? So remember that, and that's how this whole thing's going to work, and that's how you're going to see all of the patterns within this system of how it works. So you have this dot is 1. I'm going to show you how we get 39 out of the first row, okay? This dot equals 1. The entire square equals 1. This dot equals 2. And this dot equals 2. And the entire square equals 4. Each of these dots equals 3. The entire square equals 9. Each of these dots equal 5. And the entire square equals 25. So that adds up to 39. So when you're doing your calculations, once you fill this row up, you would empty it and move up to the 40. Now there's so many patterns that you can easily do calculations real quick without thinking about it, that you don't need to fill up all the holes and do all that. There's angles you go at to get your to certain calculations. So with this, it's really easy to calculate by 8. And for some reason, 8 seems to be some kind of a number that is important when you're dealing with natural organic math like this. I honestly don't know why we use a decimal system, but with the binary system of the Mancala, it's an octal system that you would count by. With this, basically, 5 times 8 equals what? 40. So you're going to find you're going to be using this square a lot, because this square adds up to 25, and then so anything over 25 that you will put in this row will fill this square up, and then you just use these other holes here for the rest of it. So each hole here equals a hole from this and a hole from this, and it's the same amount. Okay, this square here equals the amount of this square and this square, right? So what? No, hold on, I'm wrong about that. Never mind that. Okay, so with the squares, it doesn't work the same way, but with the dots, each dot is going to equal 2 of the dots that are behind it. And also, one of these dots here, you can see that there's no 4, right? So if you want to show a 4 in here, you have to put 1 here and 1 here. And I don't know mathematically why there wouldn't be a 4 in here. I don't know. I mean, I just don't understand it. I'm trying to understand it, and there's no videos out there that will show you the 40-base system like this. And I am sure that that's the way that it's meant to be used. So because we know the kind of patterns of how this works, we can basically, if I'm going to multiply by a certain amount, it's similar to the Mancala. I'm going to move forward. If I want to multiply, if I want to double it, I move forward. If I want to double that, I do that. I put 2 on there. Okay, that's going to be 4. Now, if I want to double the 4, that's going to be 8, and that's different. I have to go put 1 here and put 1 here. So you take that and you would move the rocks here. If I want to double that number that I have here, I have to go here and then put another 1 here and then 1 here. And I know it sounds weird and stupid, but it's not. And hopefully as we get into more videos, you'll see why it's not. And it's that guy was right when he said they have a superior method of calculating. The Incas do. What I just showed you, there's patterns that when you memorize them, you can use them way up here with far larger numbers. And so you can do a massive number, and you could make this as long as you wanted. And if you remember the patterns that you were using here, you can do massive calculations very quickly up here. It's very simple. If I want to multiply anything by any number over 40, my first step is to move into the hole above it. When I say the hole above it, like this hole would be the hole that's above that, right? It correlates to it. This hole correlates to that hole. So anything that I want to multiply by anything more than 40, I move it up to the hole that correlates to it. And that would be the same up here too. If I want to multiply 8,000 by 40, I don't have to think about it. What is 8,000 times 40? That's really hard. I just move it right there. There's no thought involved at all, hardly. And so whatever point you start at, you just know the amount you want to multiply and you move it up that many times. And there's patterns. Boom, 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 like that. And so there's these kind of like twisting, snaking patterns that if you do this enough, you could draw the patterns out. I've done it before, drawing the patterns, draw the patterns out. And so I know that anything I'm multiplying by 7 is I'm going to do a certain, it's kind of like gymnastics here with these rocks, right? I'm going to, and it's whatever it is, multiplying by 578 times 7. Well, I make, 578, which would be a 200, a 400, and then I have to make 100 more, which is going to be an 80, and then I'm going to have 4 rocks down here. And then so each one of those, I'm going to multiply it by 7 or by 8 or any number, multiply by 360 or 200 and whatever. There's a certain pattern that I'm going to have memorized. Anything multiplied by 6, I'm going to do with it. Anything multiplied by 10, I'm going to do with it, right? So there's certain geometric patterns that work their way out on here. I don't have them all memorized. I'm not even that good with it yet, but I wanted to share the little bit that I do know about it. And so I'm trying to introduce it to you. This paper was just to show you the values. Here's the real board. And so in the next video, I want to do some actual math problems. And I hope you come back, and I think it'll be really fascinating to watch how this works, and we can learn it together. Bye.